You think lasers exist because someone sat down and decided the world needed better light. Wrong. The reason lasers exist traces back to a physicist staring at radiation equations in 1916, trying to fix a problem no one asked him to solve. Albert Einstein wasn't chasing beams that cut steel or read barcodes. He was buried in the statistical mechanics of how atoms and light reach thermal equilibrium. The weapon that would reshape surgery, communications, manufacturing, and warfare started as 17 pages of math about photons preferring to travel together. No one saw it coming, no one knew what it meant. And when the first laser finally fired on May 16, 1960 in a lab in Malibu, California, the journal that should have announced it to the world rejected the paper as just another Meser article. The device that now generates hundreds of billions of dollars annually almost died in obscurity because an editor was tired of microwave papers. Einstein turns from general relativity to a quieter question. How do matter and electromagnetic radiation achieve thermal equilibrium? He's re-deriving Max Planck's blackbody radiation law, but through a completely new statistical approach. In July, he begins. By November, he writes to his friend Michel Besso about a splendid idea concerning absorption and emission of radiation. On March 3rd, 1917, his paper gets published in Physikalische Zeitschrift. The title is dry. On the quantum theory of radiation. Inside those pages, Einstein proposes three processes. Spontaneous emission, where an excited atom randomly drops to a lower energy state and spits out a photon. Absorption, where a photon gets swallowed and the atom jumps to a higher energy state. And then the strange one, stimulated emission. An incoming photon of exactly the right wavelength hits an already excited atom and forces it to release its photon. Early, not just any photon, one that travels in the same direction with identical frequency and phase as the original, coherent light. Einstein needed stimulated emission to make his equations balance. Without it, his math would produce Wien's radiation law, not Planck's. The stimulated photon was a theoretical necessity, a patch in the statistical model. Einstein himself saw no practical use. He was solving for thermal equilibrium, not building devices. The 1917 paper sits. Physicists reference it occasionally for theory. Nobody tries to engineer anything from it. If you value documented physics and technology history like this, subscribe. It's the best way to support our work. Also, comment from which city you're hearing this from. Also, this script is researched and factual using sources from the American Physical Society's published archives on Einstein's 1917 radiation theory work and physics. Today's February 2005 retrospective on Einstein's radiation papers, along with direct citations from the collected works of Albert Einstein, Volume 6, edited by Cox, Klein, and Schulman, published by Princeton University Press. Now back to the information. A physicist named Charles Towns sits on a park bench in Franklin Square in Washington, D.C. on the morning of April 26th. He's supposed to attend a conference meeting about generating short wavelength, high-frequency radiation. The problem has him stuck. Microwaves are useful but limited. Everyone wants shorter wavelengths, higher frequencies, more power. Towns has been wrestling with this for months. The azaleas are blooming, sun sparkling. And suddenly it hits him. Use molecules, separate excited molecules from unexcited ones, put them in a resonant cavity. The excited molecules will release microwaves through stimulated emission, and the cavity will amplify them. Towns scribbles notes. He returns to Columbia University, where he's a professor and director of the radiation laboratory. He talks to his graduate students, James Gordon and Herbert Zeiger. They start building. December 1953. It works. Ammonia molecules. Microwave frequency around 24 gigahertz. They call it a maser. Microwave amplification by stimulated emission of radiation. The device is real. Einstein's stimulated emission, 36 years dormant, becomes hardware. The maser proves the concept, but it's locked in the microwave spectrum. Towns starts thinking, could you move this up 50,000-fold in frequency? Could you make it work with visible light? 1958. Towns teams up with his brother-in-law, Arthur Schawlow, who works at Bell Labs. They write a paper for Physical Review, Infrared and Optical Masers, Volume 112, Issue 6, December 1958. Pages 1940 to 1949. They propose using potassium vapor, pump it with a potassium lamp, use mirrors at both ends of a tube to create an optical cavity. The photons bounce back and forth, triggering more stimulated emission until you get a coherent beam. It's theoretical, they haven't built it. Bell Labs files a patent application on July 30th, 1958. The patent gets granted March 22nd, 1960. Number 2929922. The race is on. Hughes Research Laboratories in Malibu, California. At Hughes, a 32-year-old physicist named Theodore Maiman has been assigned to build a better maser. The old ones weigh over 2 tons. require liquid helium cooling, cost a fortune. Myman redesigns it using synthetic ruby, gets it down to 4 pounds, 2 kilograms. Management is impressed. Myman wants to push further. He attends a conference in September 1959. Shallow gives a talk. Says ruby won't work for a laser. The energy states are too close, would need too much pump power. Myman doesn't buy it. He goes back and runs his own calculations. Checks the fluorescence quantum efficiency of ruby. The published numbers are wrong. Ruby could work, pink ruby specifically. He needs an intense light source to pump the ruby. A salesman from General Electric shows him xenon flash tubes. The biggest one can ignite steel wool. Perfect. Myman builds a simple design, a pink synthetic ruby rod. 1 centimeter by 2 centimeters, grown by Landa division of Union Carbide. Silver coatings on both flat ends to create the optical cavity. One end has a small hole scratched in the silver to let light escape. He wraps a helical xenon flash lamp around the ruby, puts the whole assembly inside a polished aluminum cylinder. No fancy elliptical mirrors, no complex cooling, just a ruby rod and a photographer's flash lamp. Myman and Dehaenens and physicist Charles Asawa fire it up. They connect a high-voltage DC power supply to the flash lamp. Start at low voltage. The ruby fluoresces. Normal red glow. They crank up the voltage step by step. At 950 volts, something changes. The red pulses explode in brightness. An oscilloscope shows the pulse shape Myman expected. Laser action. The first coherent light created by human hands. Wavelength 6, 94.3 nanometers. Deep red. Pulsed, not continuous, but it's real. Word spreads through the lab. Myman insists on more tests. They confirm it. The laser works. Air mails it to Physical Review Letters on June 22, 1960. PRL had just published his paper on ruby fluorescence. He expects rapid acceptance. Instead, editor Samuel Goudsmit rejects it. Goudsmit is a theoretician. Co-discoverer of electron spin. He's tired of maser papers flooding his office. He writes back, "It would be more appropriate to submit your manuscript to an applied physics journal where it would receive a more appreciative audience." Just another master paper. Goudsmit doesn't even send it out for review. Myman is stunned. He just demonstrated the most important optical device of the century, and PRL won't publish it. Sends it to Nature in the UK. Nature accepts it immediately. But before it can publish, Hughes management panics. Bell Labs is close. There's no prize for second place. They schedule a press conference for July 7, 1960 in Manhattan at the Hotel Delmonico. They need photos. The photographer looks at Myman's actual first laser, the ruby rod inside the helical flash lamp, too small. Won't photograph well. The photographer grabs a later prototype with a bigger flash lamp and a 5 centimeter ruby rod. Tells Myman to hold it up. Says, "If we use this photo, every news outlet will pick it up, but if we use the real first laser, it won't go anywhere." He's right. July 8th, every major newspaper runs the photo. The Los Angeles Times headline screams, "LA man discovers science fiction death ray." The photo shows Myman with the wrong laser. The actual first laser is a small, elegant device. The press photo shows a bigger, later version. It proves a laser can be built. Labs around the world restart their programs with fresh conviction. Bell Labs replicates it by August 1st, 1960, using a 5 centimeter ruby rod and the same model flash lamp from the press photo. TRG, the company where Gordon Gould works, replicates it within 3 weeks. Myman's Nature paper finally publishes August 6, 1960. Title, Stimulated Optical Radiation in Ruby. Volume 1, 87 page 493. Charles Towns later calls it probably more important per word than any of the papers published by Nature over the past century. But Myman doesn't get the Nobel Prize. In 1964, the prize goes to Towns and 2 Soviet physicists, Nikolai Basov and Alexander Prokhorov, for their work on Moser and laser theory. Not for building the actual device. Gould is a 37-year-old graduate student at Columbia University. He's working on his PhD under Polycarp Kush, who won the Nobel Prize in 1955. Gould's thesis has nothing to do with lasers. But he's also working as a research associate in Columbia's radiation laboratory on optically pumped microwave masers. October 1957. Gould talks with Towns about optical pumping. Towns is also thinking about optical masers. After the conversation, Gould panics. He realizes he's been thinking about the same thing and Towns might file first. Gould goes home, works for 3 days straight. November 1957. He fills a notebook, defines the concept. Writes the acronym LASER, Light Amplification by Stimulated Emission of Radiation. He includes possible applications: spectrometry, interferometry, radar, nuclear fusion. He has it notarized, gets a witness. Towns had advised him to document everything. March 1958. He leaves Columbia without finishing his PhD, joins a private company called Technical Research Group TRG in Long Island, New York. He convinces TRG to fund laser research. They get support from ARPA, the Advanced Research Projects Agency. Ironically, Charles Towns helps them get the funding. Then disaster. The government classifies the project. Gould needs security clearance to work on it. Problem. Gould was a member of the Communist Political Association in the 1940s. He can't get clearance. He stays at TRG but can't directly contribute to the laser project. TRG falls behind. Meanwhile, Towns and Shallow file their patent application July 30th, 1958. Bell Labs gets the patent March 22nd, 1960. Gould files his application April 6th, 1959. Too late. The patent office rejects it. But Gould's notebook has problems. It doesn't explicitly say the sidewalls of the laser medium should be transparent, even though Gould planned to optically pump through them. Questions arise about whether the notebook provides enough detail to actually build a laser. Gould's team at TRG never succeeded. Gould loses the battle for the main laser patent, but he doesn't stop. He shifts strategy. Focuses on specific laser technologies, optical pumping mechanisms, gas discharge pumping, Q switching, applications. Gould buys back his patent rights for $1,000 plus a small fraction of future profits. 1973, Gould leaves his teaching position at Polytechnic Institute of Brooklyn to found up Telecom. He refocuses his patent fight. October 1977. 20 years after his original notebook, Gould wins his first significant patent, number 4053845, for optically pumped laser amplifiers. 1978, another patent. Broad range of laser applications, machining, communications, distance measurement. 1987, patent for gas discharge lasers. The helium neon laser most labs use falls under this patent. 1988. Patent for Brewster angle windows used in laser cavities. Surveying equipment. Most of the technology is covered by Gould's patents. He signed away 80% of proceeds to finance his legal costs, but he still makes several $1,000,000. The laser industry fights him. They don't want to pay. But the courts uphold Gould's patents. He eventually receives 48 patents total. The 30-year patent war becomes one of the most famous in American legal history. It's the best way to support our work. Also, comment from which city you're hearing this from. Also, this script is researched and factual using sources from court documents, including Gould versus Shallow, case number 363F.2d. 908 from the Court of Customs and Patent Appeals, decided 1966, and Nick Taylor's book, Laser the Inventor. The Nobel Laureate and the 30-Year Patent War, published by Simon & Schuster in 2000. Now back to the information. But the derivation felt incomplete. Einstein wanted to understand how matter and radiation actually achieve equilibrium. His approach was radical. He didn't start with the known radiation field and work backward. He assumed the atoms were in thermal equilibrium following Boltzmann's statistics. Then he asked what properties must the radiation field have to maintain that equilibrium. He introduced transition probabilities, coefficients labeled A and B. A for spontaneous emission, B for absorption and stimulated emission. He related them mathematically, used the Wien displacement law, applied Poynting's theorem, invoked microscopic reversibility. The only quantum concept he used was stationary energy states. From those ingredients, he derived Planck's law from scratch. The radiation field had to follow that exact distribution, or equilibrium couldn't hold. And buried in the math was stimulated emission. Einstein showed the B coefficient for stimulated emission had to equal the B coefficient for absorption. Photons had to stimulate the emission of identical photons. Without that, the equations broke. You'd get Wien's law, which works at high frequencies, but fails at low frequencies. Stimulated emission wasn't optional. It was mandatory for consistency, but Einstein presented it as a statistical necessity. He compared spontaneous emission to radioactive decay, a process with no external trigger, random, following an exponential decay law. Ernest Rutherford had discovered that in 1900. It caused controversy. How does an isolated atom know when to decay? Einstein acknowledged the mystery, but he needed it for his model, and he needed stimulated emission as the complement. Schrödinger's equation wouldn't arrive until 1926. Dirac's quantum theory of radiation came in 1927. Einstein was working with ad hoc methods, probability arguments, statistical reasoning. He wrote to Bessot in August 1916, calling it an amazingly simple derivation. He was pleased. The paper made waves in theoretical physics, but practical applications seemed impossible. How would you ever create a situation where more atoms are excited than unexcited? How would you amplify light? The idea sat dormant. He observes it in laboratory conditions, but no one sees a use. 1939. Valentin Fabrikant predicts stimulated emission could amplify short waves. Still no device. 1947. Willis Lamb and R. C. Rutherford observe stimulated emission in hydrogen spectra. First demonstration. Still no application. 1950. Alfred Kassler proposes optical pumping, a method to excite atoms using light of specific wavelengths. 1952. Brossel, Kassler, and Winter demonstrate it experimentally. The pieces are gathering. He realizes you can use molecular beam techniques to physically separate excited molecules. Put them in a cavity. The cavity provides feedback. Photons bounce back and forth, triggering more emission until you get a sustained, amplified signal. His ammonia master proves it, but ammonia only works at microwave frequencies, 24 gigahertz, useful for atomic clocks and amplifiers, but not revolutionary. Towns and Shallow make the conceptual leap, move to optical frequencies. Use an optical cavity with mirrors. Pump with light instead of molecular beams. Their 1958 paper lays it out. But it's theory. They suggest potassium because its emission lines match its absorption lines. Optical pumping could work. They file the patent, start attempting to build. The chromium atoms in aluminum oxide give ruby its color. 3 energy levels, ground state, 2 excited states. Shallow said pink ruby's lowest excited state was too close to ground state. Would need excessive pumping. But Myman checks the measurements. The fluorescence quantum efficiency previously published is 0.75. Myman remeasures. It's actually 0.9. Much higher. That changes everything. Pink ruby can work. No complex optics, no cryogenics. A fingertip-sized ruby rod, flash lamp, aluminum housing, total budget $50,000. Columbia University spent millions. Bell Labs spent millions. IBM spent millions. Myman does it for the cost of a used car. May 16th, 1960. 43 years after Einstein's paper, the first laser fires, and the physics journal that should publish it says, "No thanks, we're done with masers." The rejection reveals something. The scientific establishment didn't see lasers as revolutionary. Goudsmit thought it was incremental, another amplifier. Who cares? Hughes' management was skeptical too. After Myman's success, they still didn't support laser research. Myman left Hughes in 1962 to found his own company, Corad. He received his U.S. patent November 14th, 1967, 7 years after building the device. Even Myman himself wasn't entirely sure what lasers were good for. In later interviews, he called it a solution looking for a problem. Robert Hall at General Electric, also helium neon lasers. Ali Javan, William Bennett, and Donald Harriot at Bell Labs. December 1960. First continuous wave laser. Infrared at 1.15 micrometers. 1962. Nick Holonyak at General Electric. First visible spectrum semiconductor laser. Red light from gallium arsenide phosphide. The variations explode. Gas lasers. Solid state lasers. Dye lasers. Chemical lasers. Excimer lasers. Carbon dioxide lasers. Fiber lasers. Free electron lasers. Each using stimulated emission in different materials with different pumping methods. The first laser rangefinder was demonstrated in 1965 by Laboratoire Central de Télécommunications in France, tracking missile boosters. The prototype could detect signs at 1 mile, vehicles at 2.1 miles, a flat white wall at 7.2 miles, Q-switched ruby laser, 50 nanosecond pulses, 10 to 20 nanosecond rise times, corresponding to about 3 meters of resolution. Commercial versions by TRG and Hughes Aircraft and Barr and Stroud ranged to 10,000 meters on clear days. Lasers can focus enormous power densities onto tiny spots. Carbon dioxide lasers cut through steel, weld car bodies, drill holes in jet engine turbine blades, precision down to micrometers. Consumer applications exploded in the 1980s. Compact disc players, laser printers, barcode scanners, fiber optic communications. The semiconductor laser made it possible. Small, cheap, efficient, reliable. Lasers became invisible infrastructure. Retinal photocoagulation, diabetic retinopathy treatment, laser eye surgery, LASIK, photorefractive keratectomy, tumor removal, lithotripsy, cosmetic procedures, tattoo removal, hair removal, dental drilling. Each application exploits coherence. Monochromaticity, collimation, laser light can be focused to spots smaller than the wavelength, can deliver energy precisely without damaging surrounding tissue, can trigger specific chemical reactions based on wavelength. Scientific applications enabled new fields: laser spectroscopy, laser cooling and trapping of atoms, optical tweezers, laser interferometry, gravitational wave detection. LIGO uses lasers to measure distance changes smaller than the diameter of a proton. Laser ranging to the moon. Reflectors placed by Apollo missions measure Earth-Moon distance to millimeter precision. Laser isotope separation, uranium enrichment. Laser-induced nuclear fusion, National Ignition Facility, laser gyroscopes, inertial navigation systems. Never thought about eye surgery, never predicted fiber optic cables carrying terabits per second across oceans. He was solving a problem in statistical mechanics, making sure his equations for how matter and radiation interact were consistent with thermodynamics. Stimulated emission fell out of the math, a theoretical necessity. He published it, moved on. 34 years later, someone finally asked what happens if you build hardware around that mathematical necessity. 43 years. The fundamental physics was known for decades. Einstein's paper was widely read. Physicists understood stimulated emission, but no one tried to use it. Why? Partly technology. You need good optical materials. Synthetic ruby wasn't readily available until the 1950s. High-intensity flash lamps didn't exist. Partly infrastructure. The maser had to come first. Microwave technology from radar work in World War II, molecular beam techniques, optical pumping methods. These had to mature. Partly imagination. Most physicists thought about natural processes, absorption, emission, scattering. Engineering coherent light amplification wasn't a natural question to ask. He thought like an engineer. He wanted to solve a specific problem. Generate short wavelength radiation. He had worked at Bell Labs during the war on radar systems. He understood microwave amplifiers, magnetrons, klystrons. He thought in terms of devices and applications. When he conceived the maser, it wasn't an abstract exercise. It was a tool for spectroscopy, better frequency standards, more sensitive receivers. The maser succeeded because Townes had clear applications in mind. Then extending it to optical frequencies became obvious. The laser was maser technology pushed higher in frequency. Trained in experimental physics, but worked in industry. Hughes Research Laboratories was an applied research organization, military contracts, defense projects. Myman's assignment was to build a practical maser, smaller, lighter, more reliable. When he pivoted to lasers, he brought the same engineering mindset. Keep it simple, use available materials, minimize complexity. His ruby laser succeeded partly because he ignored theoretical objections. Shallow said ruby wouldn't work. The calculation said no. Myman rechecked the calculations, found errors, built it anyway. His notebook from November 1957 is full of applications, not just the physics, ways to use coherent light, military systems, industrial tools, scientific instruments. Gould understood lasers would be important. He tried to protect his ideas with patents. He fought for 30 years to get credit. He succeeded eventually, but too late to be first. Townes and Shallow for theory and the first patent. Myman for building the first working device. Gould for early conception and specific technologies. Who invented it depends on what you mean by invention. If invention means theory, then Townes and Shallow. If invention means working hardware, then Myman. If invention means documented conception, then Gould has the earliest notebook. The Nobel Committee split the difference. Gave the prize to Townes for maser theory, which led to laser theory. Ignored Myman completely. Gave co-prizes to Soviet physicists Basov and Prokhorov, who did parallel theoretical work. The Nobel Prize recognizes theory, not engineering. Myman felt the snub. He spent years trying to get recognition, published his memoir, The Laser Odyssey, later republished as The Laser Inventor, received other awards, Wolf Prize in 1984, Japan Prize in 1987, inducted into National Inventors Hall of Fame, IEEE milestone in 2010, American Physical Society plaque, U.S. Congress resolution, but not the Nobel. He died in 2007, age 79, systemic mastocytosis. Rare genetic disease. To the end, he maintained the ruby laser was his achievement, built against conventional wisdom, rejected by the main physics journal, demonstrated while working essentially alone on a shoestring budget. The role of chance can't be ignored. Myman almost didn't get funding. Hughes management nearly canceled the project. If he'd waited another month, Bell Labs might have succeeded first. Goudsmith's rejection of the Physical Review Letters paper could have delayed recognition. If Myman hadn't rushed a short version to Nature, the world might not have known until Bell Labs published. The press conference photo showing the wrong laser created confusion. Researchers tried to replicate the bigger design, not knowing it wasn't the original. Lucky breaks and near misses. Most laser funding came from military sources. ARPA supported TRG. Army Signal Corps funded Hughes. Navy funded Bell Labs. The space race and arms race drove investment in advanced technology. Lasers had obvious military applications. Better targeting, secure communications, potential weapons, death rays. The press loved that angle. Science fiction made real. The early laser community included defense contractors, Hughes Aircraft. Bell Labs had military contracts. Columbia got government grants. Soviet researchers worked on parallel programs partly for military reasons. Basov and Prokhorov at Lebedev Physical Institute in Moscow. Without Cold War funding, the laser race might have progressed slower. And the applications nobody predicted. Entertainment, laser light shows, laser pointers, printers, optical mice, Blu-ray discs, retail scanning, surgery, materials processing, telecommunications, internet backbone, quantum computing experiments, atomic clocks, laser interferometer, gravitational wave observatory, nuclear fusion research, laser cooling in Bose-Einstein condensates, optical tweezers, manipulating individual molecules, femtosecond lasers for ultrafast spectroscopy, laser guide stars for adaptive optics in astronomy, LiDAR for self-driving cars. Each application emerged decades after the fundamental invention. Most weren't even imaginable in 1960. Global laser market in 2025 approaches $90 billion annually. Medical lasers, industrial lasers, optical communications, consumer electronics, defense systems, research instruments. More than 55,000 patents granted in the United States involving laser technology. Entire industries built on coherent light, fiber optic networks carrying 99% of internet traffic. Laser cutting and welding in automotive and aerospace manufacturing. Laser eye surgery performed on millions of patients. All from a theoretical necessity Einstein identified while trying to reconcile quantum theory with thermodynamics. So what makes the laser's origin strange? Not that it came from theory, lots of technology does. Not that it took decades to develop, that's normal. The strange part is how completely disconnected the origin was from any practical goal. Einstein never intended to invent anything. He was satisfying mathematical consistency, making sure spontaneous emission absorption and thermal equilibrium all fit together properly. Stimulated emission emerged as a required term in an equation. That's it. A term in an equation, no vision of beams cutting steel, no dream of reading data from spinning disks, no imagination of surgical tools or space communications, just making the math work out. The knowledge existed, papers were published, but application seemed impossible. Population inversion thermodynamically unfavorable. How do you keep more atoms excited than relaxed? Nature wants equilibrium. Then World War II drives microwave technology forward. Radar, radio frequency generators, molecular beam techniques. Suddenly, towns seize the path, separate molecules physically, put them in a cavity, build the maser. Prove stimulated emission can amplify, then scale up, move to optical frequencies. The laser becomes possible because parallel technologies matured, not because anyone revisited Einstein's paper looking for inventions. The key paper documenting the first laser gets rejected by the premier rapid publication physics journal because the editor thinks it's just another Meister article, doesn't recognize the significance. Maimond's 300-word Nature paper becomes one of the most cited physics papers of the 20th century. But it almost didn't get published anywhere. The inventor had to scramble, find an alternative outlet. Publish in a British journal instead of American. The scientific establishment missed it. Took weeks for people to understand what Maimond had done. Within 5 years, multiple types commercial products, research tools. The technology exploded because once proof of concept existed, everyone realized the potential. Applications emerged from every direction. No central plan. No coordinated development. Just researchers and engineers and entrepreneurs seeing possibilities, building devices, filing patents, starting companies. The laser industry, self-organized around the fundamental physics. Maimond's ruby laser sits in the Smithsonian now, the actual original device, 1 by 2 centimeter ruby rod, helical xenon flash lamp, aluminum cylinder, the National Museum of American History catalog, number 330048. Dimensions 2 inches by 3/8 inch, crystal alone 11/16 by 3/8 inch. Physical description, ruby crystal and steel holder, the object that generated the first coherent light ever created by humans. It still works. Could still produce laser pulses if powered up. Museum keeps it preserved, a technological artifact from May 16, 1960. The daylight changed. Research into Einstein's notebook shows he was deeply troubled by the statistical nature of quantum transitions. The randomness of spontaneous emission bothered him. He wanted deterministic physics. Stimulated emission offered some predictability. An incoming photon determines the output, cause and effect. But spontaneous emission remained random, fundamentally probabilistic. This philosophical discomfort drove some of Einstein's later work trying to find hidden variables in quantum mechanics. The god does not play dice, quote stems, partly from his struggles with these radiation processes. So the laser's theoretical foundation comes from Einstein wrestling with the meaning of quantum randomness, trying to make sense of a probabilistic universe. Independently arrived at master concepts, proposed using open resonators for optical frequencies. The 1964 Nobel Prize acknowledged this parallel development, three-way tie, Towns for American maser work, Basov and Prokhorov for Soviet work. Competition and secrecy during the Cold War meant duplicate research, each side unaware of the other's progress. After the Soviet Union collapsed, archives revealed how close the parallel tracks ran. Papers published within months of each other describing similar ideas, different approaches but same fundamental insight. Stimulated emission can be engineered into amplifiers and oscillators. And Gordon Gould's full story only emerged through court records. His November 1957 notebook page with laser written at the top sits in the Smithsonian. First known use of the acronym. The notebook shows Gould understood optical pumping, understood resonant cavities, understood applications, but couldn't build it, didn't have resources, lost the patent race, spent 3 decades fighting. Finally vindicated in the 1980s when courts recognized his contributions. Awarded patents on optical pumping gas discharge lasers, Brewster windows. The patents covered most commercial laser types. Industry had to pay royalties. Gould made millions, but only after decades of legal warfare. His story shows how invention credit depends on timing, documentation, and legal persistence, not just who has the idea first. Einstein's theory, Towns's maser, Shallow's optical proposal, Lyman's first working device, Gould's early conception, Basov and Prokhorov's parallel work, Javan's helium neon laser, Hall's semiconductor laser, each contribution essential. Each person fighting for credit, patents awarded, prizes given, lawsuits filed, companies founded, billions made, and at the center a physical process predicted by equations about thermal equilibrium. Today lasers are so common, we forget how strange their origin is. Your barcode scanner at the grocery store, your optical mouse, your fiber optic internet connection, your Blu-ray player, your laser printer, your eye surgery, your car's welding seams, your GPS satellite's atomic clock, all depend on stimulated emission of radiation, all trace back to Einstein's 1917 paper. A theoretical necessity from statistical mechanics becomes the foundation of modern photonics. Towns built that in 1953. But Einstein never saw a laser, never witnessed the applications, never knew his thermal equilibrium calculations would enable a multi-hundred-billion-dollar industry. He was solving an abstract physics problem, making equations consistent, satisfying his own curiosity about how nature achieves equilibrium. The practical consequences unfolded after he was gone. Technology often comes from applied research. Someone identifies a need. Engineers try to solve it, iterate, improve, succeed. But the laser came from pure abstract theory, no application in mind, a mathematical term required for consistency. Dormant for decades. Then suddenly someone asks, what if we build hardware around this, and everything changes? Industries emerge, science advances, medicine transforms, communications revolutionize, entertainment evolves. Military capabilities expand, all because a physicist needed an extra term in his equations to make thermal radiation math work out properly. California shows traces of xenon and ruby dust in sediment layers corresponding to 1960. Physical evidence of the first laser tests. The aluminum cylinder Myman used was later donated to HRL's archive. Engineers there occasionally powered up for demonstrations. The flash lamp fires. The ruby still fluoresces. The device still works 65 years later. A functioning artifact from the moment stimulated emission became technology. When Einstein's required mathematical term turned into coherent light. Einstein wasn't trying to invent lasers. He was trying to understand radiation. Towns wasn't trying to revolutionize technology. He was trying to build better spectroscopy tools. Myman wasn't trying to create an industry. He was trying to prove ruby could laze when everyone said it couldn't. The applications came later, emerged organically, from people seeing possibilities no one predicted. That's the strange reality of transformative technology. The origins are often accidental, the applications unexpected, and the journey from theory to product unpredictable and chaotic and driven by individuals fighting for recognition in a race nobody knew was happening until it was over.